Go. Okay, so we talked about what a derivative is yesterday. A derivative we've already been doing, right? It's that limit as h equals 0. And then we have that alternate definition. So of course, if we have one-sided limits, which we did back in chapter 2, we have one-sided derivatives. Okay. So a one-sided derivative, this formula should look familiar, right? It's just, instead of just h approaching 0, it's h approaching 0 from the right. And then this one should look the same, but this one has a minus, so that's the left-hand derivative. Okay, makes sense? So, this first example is absolute value of x. We say that it's not differentiable at x equals 0. Why not? So it has to have, in order for it to be differentiable, it has to have the same slope from the left and from the right, the same derivative from the left and from the right. Yep. If we look at the slope from the left, right, that's negative 1. If we look at the slope from the right, it's positive 1. So when these two slopes, when these are not equal, this implies not differentiable.
Differentiable, like it doesn't have a derivative?
Right. Oh, it's just the equation. Remember how is an absolute, like you can redefine absolute value as a piecewise function. So it's negative x less than 0. So if I were to actually plug into the formula, I would have to redefine this as a piecewise function. So then from the left, we plug in that. But I purposely used absolute value as an example because you can just look at it and see the slope. I just wanted to give you that as an example. So that means any graph, okay, and that's important to know. Any graph where you have a different slope from the left and from the right is not going to be differentiable. And we said if it's not differentiable, it doesn't have a derivative. So, no. Oh, it keeps doing weird things. There. So there's no derivative at x equals 0. Now, does it have a derivative at x equals 3? Yeah. So from the left and from the right, it has the same slope, right? It has a slope of 1. So it's differentiable everywhere except right here.
Wait, why? I don't get it. Does it have the same slope also coming from both sides?
So we're specifically looking at this point right here.
Yeah, so as h approaches 0 from the left, isn't the limit 0?
This is when x is equal to 0. Okay, but what if I said when, how about when x equals 3? Here. So if I'm looking from the left and from the right, aren't the slopes the same? Yeah.
It's the same.
So it is differentiable. It's differentiable at x equals 3.
Yes.
What about a negative 5? Yeah, it's differentiable there also.
We haven't learned that yet.
Okay. Question. Are you okay with that? All right, so how about x squared? Looking at x equals 0, what is the slope? From the left, what's the slope from the right? 0. How do we know that?
Because it would be a flat tangent.
Right, so again, imagine that your pencil is a tangent line, and right in the middle is your point of tangency. So as we trace along, so from the left, you're getting to 0, right? Getting a horizontal line. And from the right, you're also getting a horizontal line.
Didn't you do that for the absolute value graph too?
No.
What?
This is curved.
So you're saying you can only do that if it's curved.
Right. So some something that we're going to learn about if we have time today, something called a corner. So the absolute value has a corner. A corner just means it has a different slope from the left and from the right. And that a corner could also be like maybe you have a piecewise defined function where you have something like a line here and then a square root function. From the left and from the right, they have two differing slopes. So whenever that happens, then we know it's not differentiable.
Is that why on the problem before where we had to find the derivative graph of like
Yes,
this one?
exactly. So the previous page, when we did these, so at each one of these, and they are called corners. This is a corner, corner, corner. Each one of those points, they're not differentiable because you have a different slope from the left and from the right. Different slope from the left and from the right, which is why we use the open circle because it's not differentiable there.
So why is it closed on the end?
Because endpoints we only care about from one side. So from one side, is it like there's nothing to differ with it? You're just looking from the right here and from the left here. So we do include the endpoints there. Endpoints are kind of a little different than interior points in terms of differentiability. Okay, okay, so these two are equal, which implies it's differentiable. I know, all kinds of weird things are happening. Okay. So we know it has a derivative right at 0. Okay, so let's look at this example.
Wait,
Yeah.
So technically, since like the tangent line always keeps changing because it's a curve usually, in most points it will not have a derivative, or it won't be differential. Okay, like just follow and just choose one point on the graph that's not 0.
Okay, so 1.
Okay, and then from the other side, it's still differentiable because since it's a curve, isn't the tangent always like changing kind of like even by a little?
Right. So this is differentiable everywhere.
Okay.
There's no place on this curve where you have different slopes from the left and from the right.
Okay.
Think of it as like you're following, if you're following your tangent line, it's gradually changing. It's not like going like this all of a sudden. When we did this one, okay, so this one basically went here and then switched like that. You can't have that like jump to a different slope.
Okay.
If it's a gradual, right?
Yeah.
There was no place where it just jumped and changed to a differing slope.
Will it ever not be differential if it's not a absolute value or a piecewise function?
There are places where it will not be differentiable. We just didn't get to that yet. No, she's saying like a continuous curve. Are you talking like a smooth continuous?
X squared will ever not be.
Yeah, you can't find the derivative if there's a hole in the graph. I mean, you can't. It's not. If the point doesn't exist, you can't have a tangent line. But there are other places where we won't have a derivative. But that's 3-2. It's weird because it's like I'm giving it to you in pieces, and then we'll see like the big picture. Hopefully, that's the goal. In the meantime, let's look at this graph. So we have x squared when x is less than or equal to 0, 2x when x is greater than 0. So that's a piecewise function. Right, I'll just make a quick sketch. So it looks like this. We want to show that it does not have a derivative at x equals 0. Right, we could see. So I want, like, you may have to explain. And that's part of the AP exam that you can't, they'll say, you need to show this. And you can't just point to it and say, there's a corner, they have different slopes. You have to have the limit to support that. Okay, so let's do, I'm going to put a little minus here. So that's another way to write the left-hand derivative. So this is the derivative at 0 from the left side. So that's going to be the limit as h approaches 0 from the left of f of 0 plus h minus f of 0 all over h. Okay, so what do we end up with? If we're working from the left, then yeah, we want to work with this part. So we'll have h squared over h. Look at that. So we get 0. So the slope, so what we're saying is our tangent line from the left is approaching a slope of 0. And now from the right, we're going to prove that slope has to be the slope. Why did I write what? You sure? Positive. Okay, so now what? Right, so now if we plug this in from the right, we're plugging it in here. So it's 2h over h. So the h's cancel, and I'm left with 2. So, therefore, okay, so since these are not equal, y is not differentiable at x equals 0. Questions?
Differential just means derivative.
Differentiable, derivative are the same. You say find the derivative, and then you ask, like, there's different phrasing that you'll just have to recognize. So on one hand, I might say find the derivative, and then I might also ask where is it differentiable, or where is it not differentiable. Okay. And actually, before we look at the homework, I do just want to look at, because Bess was asking, and I think this is a good follow-up to that. How do we know it's not going to be differentiable? So how might f prime of a fail to exist? Okay, 4 places, basically. First thing, we want to make sure that it's continuous. So I had mentioned that if it's not continuous, if you have a jump, if you have a removable discontinuity, okay? If you have an asymptote, obviously you can't find the slope there, okay? So we first make sure it's continuous. So that's an example where you can't have differentiability.
But can't you technically still have another point?
Yes. So I'm looking at a specific f prime of a. I'm looking at, so this is not differentiable at x equals 0. Now, can it be differentiable at -1? Yeah. Okay, so we're looking at just one specific point. I'm just giving you like an example of what that would look like. Okay, corner. All right. This is where one-sided derivatives differ. So again, so this is not differentiable at x equals 0, right? The derivative from the left, we said, was -1. the derivative from the right at 0 is positive 1. Okay. Which we looked at previously, right? So whenever we get a differing derivative from the left and right, that is a corner. There's two more places where we can't have a derivative. One of them is a cusp. And a cusp is something very specific. Okay? And a cusp. Cusp. Is it a hard word to say without? Okay. So if we think about the secant slopes or the tangent slopes, basically these are approaching this. What's the slope approaching here? It's a negative slope, but it's approaching negative infinity from this side. We're talking about slopes now, so be careful. I'm not talking about the actual value here. The slope is approaching positive infinity. So when you have from the left, your slopes are approaching negative infinity, from the right, positive infinity. That's a cusp. And that happens when you have a rational function, even over odd, where the even is less than the odd. So like, for example, if you have 4 over 7 as your exponent, that's a cusp. If you have 10 over 11, that's a cusp, okay? So it's something very specific.
What's the difference between that and the, is the only difference between that and the absolute value and this curve? Because isn't that kind of like...
Okay, so let me explain. From the left, the derivatives are, I'm not going to put equal, but approaching negative infinity. From the right, it's approaching. It's kind of like a corner, but okay, so the difference between these is that, yes, with corners, one of them has to be approaching a real number. Okay, if one of them is approaching infinity and the other one's approaching 1, that falls under the corner category. This is very specific. This has to be approaching a negative infinity slope from the left and a positive infinity slope from the right. Then that's a cusp. It's a little confusing when you first see it. The slopes are, okay, think of your vertical line as a slope of infinity.
Yes.
Okay. Now, so do you agree these are positive slopes here?
Oh,
This is positive infinity. Do you see this is a negative slope?
positive infinity.
This is negative. Look at the slope.
Okay.
Is this a negative slope?
Yes. Yeah.
So it's approaching. No, this is positive. This is negative.
What?
You just pointed at the same thing and said
It's not my fault.
I don't get it either.
Positive infinity is supposed to go up.
Yeah, that's what I'm saying.
But it's not. The point is, from the left, we're not actually looking at 0. We're not looking at 0. I don't care when it's perfectly vertical. I care about just to the left of 0.
It's going towards negative.
This is a negative slope. This is approaching a negative infinity slope. This is positive.
Pushing negative.
This is approaching a positive infinity
So,
slope.
the y.
Oh, I get it.
Oh,
I got it.
This
This
is
is good,
the
really.
y.
Here, if you don't get it,
I got
if
I
it's
got
still just not making sense, even over odd, where the even is smaller than the odd. Just memorize that.
Better.
I don't like to, I mean, there are times where I'll just say, just memorize it. Like, I can go through over and over and over again, and some things still might not make sense. So, just take my word for it, okay? Promise you. Okay, vertical tangent is the other. When do we get a vertical tangent? That's with odd roots, like a cube root, fifth root, seventh root. Now, Eighth group. Look at this one. Now see how this one looks different than the cusp. Would you agree this is, like if I put my tangent line, is this positive slope?
Yes.
It stays positive, so it's approaching a positive infinity slope. Now from the right. Is this still positive?
No.
Is this,
Yes.
my line has a positive slope. Does it still have a positive?
Yes.
So this one is approaching a positive infinity from both sides. Or approaching negative infinity. So in other words, this one is f prime of 0 from the left is approaching positive infinity, f prime of 0 from the right. So these are both approaching positive infinity, or let's say there was a negative sign and you have negative infinity, that's a vertical tangent. Okay, these are specific. These have to be at infinity. Everything here, the only one, like these two, cusp and vertical tangent, they have to be exactly, like they have to be approaching infinity or negative infinity. These have to be, one has to be approaching positive infinity, negative infinity. The one above the corner is just when they don't match up.
So these do don't have to.
These are all places where they don't have derivatives. Okay?
If it was a cube root of x squared,
Yes. Yeah, don't forget, if you have like a rational function, you can express that with a root or in a fraction, right? So if I have x to the m over n, what's that look like in root form? It's the nth root. So there will be times when maybe I'll give you the function written this way, and you just have to kind of apply that to the same concept. Okay, so I'm not going to move on because we'll spend the next class going through the rest of the differentiability. I think that there's enough time. Oh, there's a lot of info. Okay, let's take a look at the homework. What? Did we have a chance to look at it?
Yes. I found it way too hard, so I gave up on it.
You found it way too hard, so you just gave up on it.
You'll think.
That's awesome. Thank you for that.
I tried my best.
We do 21.
Yeah, so if you didn't, well, let's go through.
I swear.
All right, so you started. Okay, page 105. This is supposed to be 12. This is where I renumbered them. So this should be. The assignment 11 was, I know, so I.
It's page 92, 1 through 4.
Yeah, and so everything's off one number. So
So
when it
this
says
should be
collect 12 through
11
14, it should be 11 through 13. Again, if you go to Haiku and look at your assignments, everything should be correct on there. Hopefully. I tried to fix everything. Okay.
So wait,
11 was that last, there was like a little assignment on the last lesson plan.
And we need to do that too.
Just by the time we have the quiz.
Oh, okay.
When do we have the quiz?
The first, which is what, next Thursday, yeah.
I already have
Oh,
the
next
quiz.
Friday, we also have the switch. So you switch with D period. So we have class next Friday also.
We do.
Because we missed, F period was affected by the holidays more than any other class. So that's why they're giving us 2 extra classes this Friday and next Friday.
Oh, so we don't have D period next Friday too.
Correct. Okay.
Knocked down with D period.
All right. So we're happy we have F period. Yay. Okay.
Oh, yeah, we would take the test then. Yeah, yeah.
All right. number 3, we're okay with that one? I'm just going to go through, like, some of these you should have been able to do. We're okay on number 3. If you didn't do it, I mean, technically we didn't finish the lesson. I was hoping you got to do a little bit of this. How about number 5? Were we okay on 5? And then we had 7. That one okay? We did one, like, very similar in the notes. And then we had 13 through 17. So what's 13? Oh, we had to... Oh, got it. Okay, so this is an example, like when we did it in the notes, we graphed our own. But I said this would be more like a multiple choice question on the AP exam where they'll give you functions that you have to match their derivative. So this one right here. Wait, 13, here, let me do it this way. So 13 is going to match up with B. Do you see these are the derivatives? Those are the original functions.
Can we just use the idea that it's just
One less degree. If you made that connection, that's fine. So like you see something that's an x squared, so that means it's going to become linear. And then like 14 looks like an x to the third. So it's going to be an x squared, so that matches A. 15 looks like a sine, or actually 15 looks like a cosine curve. Okay, so actually, no, it's going to be D.
so cosine is sine.
So
Cosine is sine.
What?
the derivative of sine is cosine. The derivative of cosine is negative sine. We'll get to all that fun stuff.
This makes much
So-
more sense after doing today's lesson.
Yeah, I mean, this is a little tricky since we haven't learned all the shortcuts just yet. But again, if you're thinking about your slopes, like this one starts out with a positive slope, so I have to start above the x-axis. Remember how we looked at the slopes and then we corresponded that to the new points on the derivative graph? You're like, yeah, sure.
Why not?
Why not? How about, okay, so we also had 17, is that correct? 17. Okay, so if f of 2 equals 3 and f prime of 2 equals 5, find an equation of the tangent line and the normal line. Okay. Well, this is just an exercise in writing equations of lines. There really wasn't anything to find. F prime is what? That just means my slope. So I know m is equal to 5. F of 2 equals 3. That means I have the point 2 comma 3. Now they wrote theirs in slope-intercept form, but again, I'm fine if they don't specify. You can just write y minus 3 equals 5, and then x minus 2.
Isn't this just the previous chapter?
Yes, they're just, the only thing they're doing, that's why I said a lot of this is overlap from what we've learned previously. It's just because they want you to get used to the notation and the terminology. We haven't used the word derivative yet, or differentiability. This is the first time we've heard that in this book. We haven't seen f prime before, so we're just recognizing that f prime of 2 is just referring to the slope of the tangent. Okay? And then for part B, so I would just write, I wouldn't go to the trouble of what they wrote. I would just leave it like this. I don't need to see this, the slope-intercept form. Moses? Oh. Is that okay now? I mean, it wasn't intended to be a difficult question. They just wanted you to recognize that notation. Okay. All right. Wow, we might actually get through all the homework. I mean, if you didn't do the first few, go and do them, but let's take a look. 19, did you guys get that far?
Yes, didn't get it.
Yes, didn't get it. Okay, so let's read. What do we have? Find the lines that are tangent and normal to the curve y equals x to the third at the point 1, 1. Okay, well, the good news is they already gave us the point. What do we need to find? Yeah, we got to find the slope. So we did x to the third, I think, in our notes packet, didn't we? Did we do the... So what we want to do is f prime of 1. That's for this function next to the third. Are we okay? I think I should just write this on the board. So it's f of,
Oh, I know what my problem
oops, hold on. You know what your problem was on this one?
is. It was distributing out for the x to the third.
Yeah, because it's going to be 1 plus h to the third minus 1 all over h.
This is the 1, 3, 3, 1, 2, 3 triangle.
Yeah, that's the Pascal's triangle, if you remember it. There's also something called binomial theorem. Did you get the binomial theorem?
Yeah.
Oh yeah, because you talked about the C thing, the combination. Okay, so what's this look like once we've multiplied it out?
H to the third.
You don't know? We just,
I'm gonna assume it's 3.
Yeah. One of the other friends.
What's a Pascal? Put my faith in there. Pascal.
Blaise Pascal. Okay,
Blaise
that's his first name, in case you're wondering.
That's my dad.
What do we get when we multiply? Don't just give me 3. What is it? It's 1 plus 3h plus 3h squared plus h cubed minus 1. Thank you. Right, and so the 1s are going to cancel. I can factor out h. And so the limit as h approaches 0 becomes 3. Now, what does that represent? That is the slope of the tangent. So I have the point 1, 1. I have a slope of 3. Can you find the equation of the tangent? I hope so. And again, if you left it in point slope, fine. B, what would we have to do with that slope?
Flip it.
And change it to
Negative.
negative.
Wait, why is it plus 4/3?
I will look. Did they make a mistake in the book? There are mistakes from time to time.
No,
That's right.
It's just in the other form. It's the other form. You don't even have to.
So let's, oh, because it's y minus 1 equals negative 1/3.
What? Oh yeah, I've heard about that.
So when I add 3/3, I get 4/3, right? Okay. All right, that was 19.
21.
Okay, how?
Grant had a question on it.
Okay, so 21. The viewing window below shows the number of daylight
That one was difficult.
in Fairbanks, Alaska. Okay, so we have 365 days, right?
I think.
And these, how many spaces are there? It looks like those are
I'm gonna
monthly.
say there's 12.
There's 12 for 12 months.
Oh, why was right?
Okay. So answer the following questions by estimating the slopes. Okay, so the first one says what? On about what date is the amount of daylight increasing at the fastest rate? What are we looking for?
The slope, the highest slope.
The steepest slope. Okay, do you understand why
The
we're
highest
looking
slope.
for the steepest slope? Because we want, whenever we see at what rate it's increasing, we're looking for the slope. And when is it the fastest? That's the steepest. So probably like here in the middle. So they said April 1st. I don't know. You could, let's see if this is January, February, March. Yeah, I mean, I guess anywhere between March and April. It's hard to determine. What do you think?
What is the rate?
Is there gonna be
April.
I mean, they said sometime around April 1st. If you said March 25th, I would be fine with that.
Oh no.
If you want to just write down what the book has, that's totally fine. I just want you to recognize how they got somewhere around that vicinity. Does that make sense? It's the steepest there because it's starting off, close to like a horizontal, then it's getting steeper, and then it's getting more towards the horizontal. So we want the steepest slope. Okay. What is that rate? So how would you approximate the rate? Yeah. Okay. So if they're using right here, you could approximate that curve, maybe.
It's like that.
So you have to, and that's where I said if like they have the month, each each of those little spaces is a month. They came up with 1 6 hour per day. Okay, if you came up with something, again, this is approximation, so if you came up with something a little different, that's fine. Do there appear to be days on which the rate of change in the amount of daylight is 0?
Yes.
Yeah, that's again, that's looking for what?
Slope.
Horizontal tangent.
Beginning, the top, and the end.
In there, you see that? On what dates is the rate of change in the number of daylight hours positive versus negative? Where is the slope positive?
July 1st.
Perfect, and then negative. You see that? Okay with that? All right.
Why doesn't it have December 31st as a day where the rate and the change is 0?
Because it's January 1st. Doesn't really matter. They just moved
Oh
it to
yeah,
January
because
1st.
Just want to make sure.
if you included December 31st, it's fine. They're just basically saying this. It's like
no,
one.
I just want to
Just
make
pick-
sure that
yeah.
there's like no.
If you
rule
had
of
December
last
31st
30
and not
days.
January 1st, that would be fine also. Does that make sense? Why? Do you
Yeah,
understand?
because it's 1 day apart,
Okay.
it doesn't really matter.
It doesn't matter. It's an approximation. Which one do you want? You want January 1st? Great. You want December 31st? Great.
I won't vote.
All right, how about this one? So 26, we had one like this in our notes. What's the function's derivative look like? Did we get to this one?
Oh, the little circle. No, first it's closed circle.
So how do we start out? We're going to use the same, here's the key, use the same x-axis, okay? So it went from -4 to 6, so just make sure you have from -4 to 6.
You find the slope of the first segment.
Right, and then what are the y values? They're going to be the slopes. It looks like this is like our steepest slope, but I'll just, I don't know, 1, 2, 3, 4, 5, 6. So the first one has a slope of, looks like up to
Over 4.
over 4 to 1/2.
Yeah, that's it. Oh, closed circle.
Closed circle, we'll start with closed.
And then something, and then open.
And then open. So just right in between 0 and 1. And then, let's see, we go down 1, 2, 3, 4 over 1. So that has a
4.
slope of
4. Oh,
negative 4. So,
Open circle.
bless you. And it just goes from 0 to 1. It's just a short segment. And then what's the next one?
0.
So from 1 to 4, we're going to put a line on the x-axis. Just make it a little darker. Okay, and this one has a slope of, so it goes up 1, 2, 3, 4, over 2, so that has a slope of 2. So at 2, does that make sense now? We're okay with those? All right, now there's another question, which hopefully after what we did today, we can answer a lot more easily. What values of x between -4 and 6 is the function not differentiable?
Oh, I
0,
got it.
1,
0, 1, 4.
Perfect. At x equals 0, x equals 1, x equals 4. Good. Makes sense because we have those corners now that we know a little bit about that. What's next? 39 to 42. We had trouble? 39? Did we get this far? No. Some of us, yes.
Yeah.
I said, did we get this far? And there were a couple like no's and some like this. You got this far?
Yeah, I did.
Okay. 39? Do we have a question on 39?
Yes.
Okay, so I want to find f prime of 1, and it's 3x squared. So what's that look like?
Wait, no.
Oh, did I read the wrong one?
No, I'm okay. Ignore me.
Oh, 1 minus 3x squared. Sorry, yeah. Now, I don't want...
That was Daniel. Daniel, chill, dude.
Jonathan?
You mean Dito? What?
I don't know. Okay.
I'm sorry. It's just I'm tired. I'm really tired.
If that's what you say.
I did get a ticket.
I was gonna say, you didn't get another ticket, did you?
I did. No, I'm just kidding. My mom would have killed me. I wouldn't have been here.
Yeah, she got the first one.
Okay, so you're just plugging into that formula. A multiple choice, there are times when there is no work and you could just write the letter, but because we haven't learned the shortcuts yet, don't just guess A. I want to see a little bit of work with that. Okay.
I'm gonna guess B. Don't kill me.
Mm-hmm. All right, what else do we have? Are you okay finishing that one? 39 to 42.
42 is the stuff we just learned.
Yeah, so this is just what we did, the left-hand, right-hand derivative. 42. Do you want to look at any of, we have like 9 minutes yet. So again, number 40. Now, I would say 41. 41 I don't need any work for. Why?
Because it's multiple choice.
Oh. I want some work for 40, not for 41. Why? Look at the right-hand derivative. What is this? Y equals 2x minus 1.
So they're both -1.
Right? I have
Nope.
no idea. I'm going to talk to this side. Okay, so what's the slope of y equals 2x minus 1?
2.
2.
2.
So I don't need to have any work for that one.
Because
Because from the right, we're looking at y equals 2x minus 1. Right there is m. And again, when I say right-hand derivative, I'm talking about the slope from the right-hand side. Now, the left is x squared minus 1. So that takes a little bit of algebra when you do the limit. So we're going to do the limit as h approaches 0 from the left. So it's going to be 0 plus h squared minus 1. And then minus -1, so plus 1 all over h.
In this case, x equals 0 would not be differentiable.
Correct. This would be a corner. So this gets us to h squared over h, which ends up being 0. We're okay with that? All right, next. Okay, so this one. Yeah, this one has a lot of parts. It's not that it looks worse than it actually is. 'Cause, like for part B, I don't need to see work for this. Again, why not? Because the slope is right there. But from the left, I'd like you to do the derivative with the definition. Does that make sense? So work for this one. No work here. Are we okay with that?
Yes.
Now, if it says find f prime of x for all x less than 1, that means I'm coming up with a formula for that. Why is this not erasing? There we go. So for part A, if I do the limit as h goes to 0, so it's going to be x plus h squared minus x squared all over h. And this is, oh, this is for 1 from the left. Actually, we can, it's fine. It's fine. I see how they did that.
So is it as h goes to 0 or as h goes to?
As h approaches 0 from the left. So the definition of the derivative, we're still going to use the h approaching 0. I'm not going to, I would say just ignore that for right now, because what we want because the curve on the left-hand side is constantly changing. So I'm not saying at x equals 1, I'm saying when x is less than 1. Because like at negative, so at 0 it's going to have a different slope than at negative 1. So I want to be able, so that's why I have x here and not 1. Because this is not just equal to 1. I mean, we might plug it in at some point, but
So for A,
this is what we're doing, the left-hand derivative at any value of x. Don't worry about the 1 part necessarily. The only reason they had to give us x is less than 1 is so we knew to use that function. It's a little confusing. Did everyone hear that? Why did they have to give us x less than 1? So which part of the piecewise function to use in our limit definition? So we had to use the x squared. Okay? And then multiply out x plus h squared minus x squared.
At this point, can we just do 2xh plus h squared over h?
Sure, just maybe on a quiz or test, just do a little supportive work. So I can see that you just didn't memorize that that's what we've been doing over and over again. But it is, yeah. So here, there's our conclusion. You notice here I said that you don't need to do any work for that. It's 2. Now, how about approaching 1 from the left? Which one do we plug into? Okay, we plug into the one right above it. Does that make sense? Why? Because it says 1 from the left, so we should be plugging into the derivative part. Sometimes it might help to do this, too. I can do this. F prime of x. I can rewrite f prime of x also as a piecewise function. I think that that's helpful. So we already said this is going to be 2x, x less than 1, and this one we said is 2, x greater than 1. When we write the derivative as a piecewise function, we just drop any of the equal to parts. Because remember, we had open circles when we did the graph of the segments. That's why in the piecewise function, we just drop all equals and just write less than and greater than. Do you understand how I set that up? So then maybe when you're doing this part, it might make a little more sense. So 1 from the left, so I'm going to plug 1 in here. I get 2. 1 from the right, plug in here, I get 2. So does that exist? Does the derivative exist right at 1? Yes. The two-sided, they're both the same.
what about F and G?
Okay. Use the definition to find the left-hand derivative at x equals 1 if it exists. Oh, we kind of already did that, so. Wait, this one says, use the definition of the left-hand derivative of f at x equals 1. Oh, I see what they're saying. They're saying go through this whole process again, but plugging in 1 for x.
Why doesn't
G wouldn't exist because it's greater than. But it says the left-hand derivative and the right-hand derivative does not exist, so it does exist.
because isn't that
No,
because
okay, this is the limit of the okay, I think we're reading this. The C and D are the limits of the derivatives. Let me see here. From the definition of the right-hand derivative.
is that because according to the piecewise function there is no x equals 1 from the right?
Yeah. No. Let me think about that.
Because from the right
Okay.
x will never equal 1.
The right-hand. Let me think about G and H.
For your extended weekend,
Yeah,
that's
sure.
all you have to do. It's your homework. Remember?
Yeah.
Think about G.
No, I'm just looking at G and H. So you just have to, you have 44 left.
We get our test.
I know, unless I write a new test. I could do that. Do you really want your tests?
We just give them back.
Do we have time?
Yes.
If
We
you
have 2
want,
seconds.
I could show them to you, but
I like, oh, it's 8:55. All right, if you want to see it real fast, I'll grab them, and if not, I will see you guys for a while. Let me go grab them. Can I have somebody erase? So Emma, you want to see it?
Emma, did you leave your homework? You did?
Oh,
pause my
Bye.
video.
but they wouldn't